Alright, so in this video we'll basically be discussing more examples on understanding Lenz law and in fact try to master it. I'll give you good enough problems for those. Alright, so yeah, the Lenz law, just a quick reminder, says that the induced EMF is always in such a direction such that it opposes the changing magnetic flux. You know, the EMF in fact arises as a result of changing magnetic flux which created the EMF. So I'll read this again. The induced EMF is always in such a direction that it opposes the changing magnetic flux which created the EMF itself. So EMF opposes its own creator. So induced EMF should oppose its own creator, meaning, and who's the creator? The changing magnetic flux, right? So if the flux is, say, increasing, the induced EMF will try to reduce it, and if the flux is actually decreasing, then the induced EMF will try to increase it. Alright, so let's say this case right here. For a change, I have taken the south pole is facing the bar magnet, south pole is facing the conducting loop. This blue conducting loop you see is just a conductor. It does not have any current in it, right? But as a result, if I move the bar magnet in a certain way, then it is going to have some current thanks to changing magnetic flux. Let's say in this case we are moving the bar magnet in this direction. Let's give a velocity in this direction. Alright, now we know that flux is a scalar quantity, but there is such a thing, please listen to this part carefully, there is such a thing as positive flux and negative flux. There is such a thing as positive flux and negative magnetic flux. Now how do we decide which is positive, which is negative? Any flux which is entering is positive and any flux which is leaving a given surface is negative, right? So if you see from this side, if you see from, you know, if you're standing here and watching, if you're standing here, this is your eye, and if you're watching from here, to you this is the leaving flux. You see these lines that are that are arriving at south pole here, that are arriving at the south pole here. All these arrows or all this flux is actually a negative flux because that is leaving the surface, right? So what you have closer to the current loop is a negative flux. Alright, so remember that. So you have a negative flux. Alright, with the flux coming out of the ring, if you move away from the ring, forget away, I'll take the away case maybe later. Let me take a towards case itself. So with this, if let's say you're moving actually towards the loop, let's say you're moving actually towards the loop. Alright, so if you're moving towards the loop, I am thinking that more and more lines will be coming out of this ring. That means the negative flux is increasing. I repeat. One moment the bar magnet is here, next moment say the bar magnet gets closer and is over here somewhere, right? Actually I should have drawn it right near that bar magnet, but you know, due to space. Let's say a while later it has moved closer, except it is still here only, right? So if that happens, I'm thinking more and more field lines are going to cross through the loop and then enter the bar magnet like this, meaning flux is increasing. I agree, flux is actually increasing, but is it the positive flux which is increasing or the negative flux which is increasing? I'm thinking it's the negative flux which is increasing, and since the negative flux is increasing, it in turn means just this, that the flux is actually decreasing. Negative flux increasing means what? Flux is decreasing. Alright. Hey, why are we doing all this? We have seen already in the previous videos the 4 steps we had to go through to identify the direction of EMF. What are the 4 steps? Identify, number 1, identify the direction of original magnetic field. Identify the direction of original magnetic field, then see if the flux whether it is increasing or whether the flux is decreasing. Then identify the direction of induced magnetic field, and finally identify the direction of current. You have done the first two right now. You have seen the direction of magnetic field. What's the direction of original magnetic field? Original magnetic field is in this direction. BO is in this direction, this arrow right here. Why? Look at the arrows. It's obvious, the white, all these arrows, the magnetic field, original magnetic field is to the right of the diagram. Alright, that is established. Flux is it increasing or decreasing? We have already established that it is decreasing. Actually the flux is increasing, but it's a negative flux which is increasing, meaning flux is actually decreasing. Alright, so flux is decreasing. So this is not the case, this is the case. Flux is decreasing. With the decreasing flux, now the Lenz law kicks in. So if the flux is decreasing, what should the induced magnetic field do? The induced magnetic field should in fact try to increase it, meaning the magnetic field should be to the right itself, right? So induced magnetic field should also be the purple line you see right here. That should be the direction of the induced magnetic field. That means induced magnetic field should be to the right. And for the induced magnetic field to be on the right, what should be the direction of current? That's right. The direction of current should be something like this. The direction of current should be something like this. Meaning the current actually is going in at the bottommost point and is coming out at the topmost point. Right, using right hand rule basically. So you will be holding the ring to identify this current. In fact, you will be holding the ring with the fingers in the direction of current, and the thumb therefore gives the direction of induced magnetic field. So we went through these 4 steps and identified the direction of current to be in, let's say this is the viewer again, anti-clockwise direction. This viewer with the eye over here will see that current as anti-clockwise, this current. All right, yeah, I hope that is clear. This is the first example of this video. I have actually more interesting, and wait, just a second. In fact, in one of my previous videos we have discussed exact same establishment, except instead of south we had north pole facing. Everything was still the same. Velocity was still towards the left, ring was still placed perpendicular like this, but the north pole was facing the conducting loop and moving closer. In that case the current was opposite, right? So if this example was a little overwhelming to you, what you can in fact do is, whenever you come across a bar magnet whose south pole is facing, and say you're not, you've not really got the grip of what to do when south pole is facing, then don't worry, face the north pole. Let's say you've mastered how to deal with the north pole of the bar magnet, right? So make the north pole face and still move it in the velocity as given in the question. Identify the direction of current using Lenz law and just reverse that. That will be the direction when the south pole would be facing, right? So if you have mastered north, you can just reverse the direction of current. So that's a little trick you can use. Otherwise, the good old Lenz law is always there to help us, right? Yeah. Let me take another example. This actually is a classic example. Let's see. We have a region of magnetic field. We have a region of magnetic field in which the magnetic field in fact is directed like that, inwards. So it's a uniform magnetic field, unless I mention, I usually forget to mention, but unless I mention that it is non-uniform, all my diagrams are actually uniform magnetic fields. Alright, so I have a uniform magnetic field of field strength, whatever. Field strength is, let's say, B, directed inwards. Alright, in this region we are bringing a circular loop of conductor, and the loop of this conductor lies in the same plane as the magnet itself, as the magnetic field itself, right? So I have a conducting loop like this, no current in this loop yet, right? So and with all this setup, let's say we are moving this conducting loop inside the region of magnetic field. So maybe a while ago the loop was here, I've been moving it for quite a while, and now I have reached this situation where it is partly inside and still moving. We are still moving this circular loop inside the region of bar magnet. I'm sorry, not bar magnet, inside the region of magnetic field. The question is, if we keep doing this, what is the direction of current in the loop? And the answer, what is the direction of current in the loop is the question. Direction of current in the loop. Alright, what is the direction of current in the loop? Answers are only two, nothing. Clockwise, B anti-clockwise, and maybe C no current whatsoever. And maybe we can give an option D as not enough data. But looking at my hesitation, you already know that answer is going to be one of the first two options only. Anyway, let's try to figure out, but still that's a big question, clockwise or anti-clockwise. That's a big question, right? So first of all, I think let's at least make sure that it's not C, that there is no current, right? Like there will be actually current is what I'm trying to say. All right, so if it is moving inside, I'm thinking right now, the very moment this image is taken, let's say this snapshot is taken, when this much of area is inside, right? So the magnetic flux at this instance would be magnetic field strength B into that area. Let's call the present area as A1 into cos theta. Cos theta actually is 1 only, because area is lying on the loop, so area vector is perpendicular to the plane. Area is lying on the plane, so area is perpendicular to the plane. Magnetic field is also perpendicular to the plane, so angle between the area vector and the field vector is 0, therefore cos theta is 1, so I don't really have to worry about this one. But flux right now, let's call it flux phi1 at this very instance is B into A1. Alright, a while later, let me calculate flux phi2. Maybe at that stage, I'm thinking that a little more of circular loop would have entered the region. Maybe a while later, if I go back and see it, maybe the loop would be more inside than it is right now. And then what is changing? Is the magnetic field changing? No, but I'm thinking the area is actually changing. Now the area through which the flux is passing is this area, and therefore the new flux would be B into A2. Magnetic field is not changing, B into A2, and clearly A2 is greater than A1, right? So much of math, forget, like if it is too much of math for you, just focus on this. Clearly the area is increasing, and therefore clearly the flux is increasing, right? And if the flux increasing, that is your step 2 completed. Step 1, identify BO. Step 2, find if the flux is increasing, and we have already established that in this case flux is actually increasing. What's the direction of magnetic field, by the way? Original magnetic field is directed inwards. That is already given in the question. So BO done, flux increasing done. That brings us to third step, identifying the direction of induced magnetic field. Now that the flux is increasing, the induced magnetic field should be such that it should try to decrease the flux, meaning the induced magnetic field should be in the opposite direction to existing magnetic field. So induced magnetic field would be like this. Actually, I'm drawing too many dots so that you can actually see them. So induced magnetic field should be in this direction. The dot meaning towards you, outside the screen, perpendicular to the screen and outside. And how do we get the magnetic field towards you? Only by having current in this direction. Only if I can have current in this direction. If I can have current in this direction, the yellow lines, only if I can have current in that direction can I have magnetic field coming outside. Alright, so therefore the answer to that question, what's the direction of current, is anti-clockwise. Answer is anti-clockwise. All right, let me take another very interesting. This third question is my favorite among all. All right, so let's see. We'll try to do something new here. So I have a circular ring, conducting ring, of course. Again, I have a conducting ring, and that conducting ring, we have placed it near a very long conducting wire. There is a very long conducting wire which actually carries a time dependent current. So current over here is a time dependent function. All right, such that the current increases with time. The current increases with time. Current increases with time. All right, so and this is a long wire, by the way. This is a very long wire. All right, and there is a circular loop of radius r placed pretty near to it. Question is, if the rod has the current, if the circular loop establishes the current, the direction of current, is it going to be anti-clockwise, option A, or clockwise, option B, or no current, option C? No current, option C, right? We will try to answer this. This is my favorite. If you like, you can just pause and try this once. All right, again Lenz law, but Lenz law works at its best here. All right, so 4 steps. I'm very eager to mention the 4 steps here. So for the maybe for the last time, this is probably going to be my last question unless I have enough time. Let's see. So first step, identifying the direction of original magnetic field. You know, these, so far in all the questions I have taken, the first 2 steps have been very lame. It was very obvious that in the original magnetic field was already given in the question. Look at this for example. Direction of original magnetic field is already given, bunch of crosses. Flux increasing or decreasing, pretty simple. The first 2 steps were very simple for us in all the examples I have taken, right? But the first 2 steps are actually, you're going to have to choose the first 2 steps also very carefully here. Let's see. I'm excited for this. So yeah, BO, original magnetic field, identifying that direction. Second, determining whether the flux, whether it is increasing or whether it is decreasing, right? We'll identify that. And third step obviously is based on whether the flux is increasing or decreasing, we'll identify the direction of induced magnetic field. This induced magnetic field will be a result of induced current, but we'll be working backwards. We are actually working backwards here. We are working reverse. So it is the induced current. I'm sorry, one second. It is the induced current which gives induced magnetic field, in fact, but we are working backwards. So what we'll do first is we'll identify the induced magnetic field and then we'll come to induced current. All right, so let's go through these steps one by one. So let's first do this, direction of original magnetic field. Now that is actually very, not very clear in this question. At least we will come back to the increasing current later. That doesn't even matter right now. All that really matters right now is the direction of current. Clearly current is in towards right. So current is in this direction. With the current of a long wire in this direction, the direction of magnetic field over here where the ring is placed, would it be inside or outside? You're right, the direction of magnetic field will actually be outside. If you have any doubt, you can actually check out the section where I've discussed direction of magnetic field due to a straight long wire, first application of Ampere circuit law. Anyway, how do you find? Grab the wire, the long wire, with your right hand, with the thumb in the direction of current and the curled fingers give the direction of magnetic field. The fingers will actually be going in, so magnetic field lines will be like this actually. So magnetic field will be concentric circles like that, and over here the current magnetic field will actually be coming out. So yeah, first step is done. Original magnetic field is outside. All right, great, great. And just to, for safety maybe, I'll write the expression for magnetic field. Magnetic field is mu naught I. This is again a result of magnetic Ampere circuit law. We have derived this in Ampere circuit law. Mu naught I by 2 pi r. 2 pi r. R is the distance of the point where you want to find the magnetic field from the straight conductor. 2 pi is just a constant, mu naught is also a constant, but I, in this case, in the present situation, the current which is causing the original magnetic field, is that constant? I don't think so. Current is increasing, so magnetic field is increasing. If the magnetic field is increasing, flux, my friends, is also increasing. So decreasing case is gone, so flux is increasing. First two steps are now done. You have to think a little, and only then could we answer the first two steps. But from here onwards, it's again the good old Lenz law, right? So if now that the flux is increasing, the induced current should oppose the original magnetic field. And what was the direction of original magnetic field? Original magnetic field in fact was outside. So induced magnetic field should be inside. I'll just mention that here in the diagram. So just right beside it, I'll draw that the induced magnetic field BI should actually be directed inside. And for the last step now, what should be the direction of current in the loop such that the induced magnetic field is inside? Now that is pretty simple. The direction of current should be clockwise. Direction of current should be clockwise, right? So answer to this question is clockwise. This question can be asked in different ways, like this case. Let's call this case A. Anyway, for this question the answer is clockwise and your answer is done. What if the question was this? Current is a time dependent function, except it is decreasing with time. And if that was the case, your answer would have been anti-clockwise. If it was decreasing with time, your answer would have been anti-clockwise. So option A is answer for question B. This is question B. This is my question B, right? And option is B for question A. And one more way I can ask this question, like C. Current is constant. That current in the long wire you see is actually constant. In that case, what would have happened? If the current were constant, I'll pay attention to this expression for a minute. If the current is constant, then magnetic field itself is constant. So if the magnetic field is constant and area is constant, so field is constant, area is constant, angle is constant. So how will the flux change? Flux is not going to change if the current is constant, therefore, right? And if the flux is not changing, there is no question of induced EMF, and therefore there will be no current. So for part C, if the current in this wire, if the current in this wire is constant, then there will be no current in the loop. So this is the answer for question C. I have messed it up. I mean, I've overcrowded this region, but if you're listening carefully, I think unless I've made a silly error somewhere while explaining, you should have understood this. All right, yeah. So I don't think there is any mistake here. Yeah, great. And if there is at all, I'll just post it while in editing. All right, great. I hope that helps. In the next video, we'll discuss about motional EMF. All right, thank you.